Okay, so we will start from where we left yesterday. That is, we want to optimize the error function such that it is minimized. Okay, but before going ahead and proceeding, I would like to share a few points with you that we discussed what is M, but its geometric intuition is its slope. So if slope is high, that is if M is large, the regression line will be a steeper one. Okay. And if M is small, our regression line will be flatter. So what is its intuition? Its intuition is that if M is more, so a small change in CGPA will impact the package massively. Okay, so if this is the change in the package when CGPA increased by little, but when the M is small and this curve is flat, you will see that there is not a large change in the package of a student, when CGPA increased. Okay, so this is the geometric intuition of our M, that is the slope. Okay, second thing is that we discussed that the error equals to summation yi minus yi hat. But the issue with this representation of error function is that uh, suppose there is a point this and another point this. Okay, and suppose the distance or the error of both is 5. Suppose this was 5 LPA and this is 10 LPA, and suppose this is 0 LPA for now. Okay, these are hypothetical figures. So when we calculate our error, that is yi minus yi hat, so and its summation, this will lead to 0 because if I subtract y1 from y1 hat plus y2 from y2 hat, this implies n minus 5 plus 10 minus 5 plus 0 minus 5. This is 5 minus 5. This is equal to 0. But it is obvious that error is not 0. We can't say that our regression line is passing through all the points. Okay. So either we take the mod of this error function or we square it. yi minus yi hat whole square or modulus of yi minus yi hat. Okay, but okay, so we are taking this function, and the reason for not taking the modulus and taking the square is that the graph of modulus is V-shaped and it is not differentiable at this point. Our aim is to minimize the error function, and we will achieve by differentiating it with respect to M and C or M and B intercept. Okay, but in our mod function is not differentiable at 0. So we cannot take this model or function as our error function. So our new error function is summation yi minus yi hat whole square. I hope I am clear to this point. Okay, so we need to minimize our error, and my error function is summation yi minus yi hat whole square. Okay, so first I will differentiate. I will write my error function as summation yi minus mxi minus b whole square, because yi hat equals to mxi plus b. Okay, so I want to minimize this function. First, I will differentiate it with respect to m, or b, you can take it and put it equal to 0. So dE by dm is equal to, first, okay, let's start with b first, because we will need this value of b lit. Okay. Oof. Huh. Okay, so the differentiation would be like this: partial differentiation sum 2 summation yi minus mxi minus b multiplied by, since m will be constant and this term will be constant, we will get minus 1, and this whole is equal to 0. So I can write it as summation yi minus mxi minus b equal to 0. Since I take minus 2 here, minus 1 outside, and put it equal to 0, equate it to 0. And after this, I can write it as yi minus m summation xi minus b into n. This is equal to 0. And if I take b into n on the right side, b into n equals to summation yi minus m into summation xi, and b is equal to summation yi minus some m into summation xi whole divided by n. So we will see that here, when n is divided by the summation yi, it is mean of y, and when summation xi is divided by the number of terms, it is mean of x. So we will write b is equal to mean of y minus m into mean of x, and this is my value of the intercept where error function is being minimized. Okay, this is my first result, that when I want to minimize my error function, I have to use this function or put b is equal to this value, where so that my error function is being minimized. Second, now I will differentiate it with respect to my error function with respect to m, and my error function is yi minus yi hat whole square. This is equal to yi minus mxi minus b whole square. Okay, and I have the value of b which I can put here. So my new error function is summation yi minus mxi minus mean of y plus m into mean of x. Okay, now and here we have whole square. So when I differentiate this one, partial differentiate this function with respect to m, what I will get is 2 summation this whole term as it is minus mxi minus y bar plus mx bar multiplied by this term will cancel out. I will get minus xi from here, and this will cancel out, and I will get plus x bar. This is in multiplication. Okay, so now we move ahead, and I put it equal to 0. And if I take this minus out, so I will get summation yi minus mxi minus y bar plus mx bar multiplied by x bar xi minus x bar, and this is equal to 0. Now I will take m common from here, summation yi minus y bar minus m xi minus x bar, and this is in multiplication xi minus x bar. This whole term is under the summation, and if I multiply it with both of these terms, this is equal to 0 summation yi minus y bar into xi minus x bar uh, minus summation m xi minus x bar whole square. This is equal to 0. So I can take m out and send this term to the RHS. This will be equal to m summation xi minus x bar whole square is equal to yi minus y bar into xi minus x bar. And from here, I will get my m. That is the slope equals to yi minus y bar into xi minus x bar whole divided by xi minus x bar whole square. And this is my result. This is the value of m for which my error function will be minimized. When this and with the help of this b is calculated, I will get my error to the minimum point, and the equation for b was y bar minus mx bar, and this is the result. When we use both of these terms to calculate my y pred, that is the y prediction, the error will be the minimum. Okay. Okay, so now I want to give you the intuition of how my error function is looking. What is its graphical representation? Error equals to yi minus yi hat whole square. Now I will suppose that my b is equal to 0. That is the intercept is equal to 0, and my regression line is passing. I'm sorry. And suppose this is my regression line. Okay, and these are my points. Yeah. So uh, this is my CGPA, and this is my placement. Correct. So when I plot this error function, and what I mean by plotting this error function is that here I have my slope and here I have my error. Okay. So you will see in that my slope is yeah. So when I have this slope, which is the theta, and it is very small, I am getting very large errors. You will see that the distance of these points is very large, or when I parallelly plot these, I am getting huge errors in my model. So I can plot this as my error. Now suppose I increase the slope of my line, and now suppose this is my new regression line. Okay, so now you will notice that the errors in my model are reducing. So earlier I was getting this point, but now I am getting around this point, and my error has reduced. Okay, so I can plot this here. You will notice when as I keep on changing the slope of my model, the errors will keep on reducing. Okay, and if I don't stop here and keep on changing the slope of my error of my model, you will again start seeing that the errors are again starting to increase, and the graph will and the error will be plotted like this. So I get this parabola function, which is my error function, and this is the point where my errors are minimized, and this is the point which I am searching for through my M and B. When I change my M and B, there will be a point of minima which I want to find. Okay, so now I have planned that I will show you this model y equals to mx plus c through an implementation of scikit-learn code, that is ML. Okay. mm, yeah. So now our goal is, first we will see how our line regression line is changing when we change the value of m and c. Okay. And then what we will do, that we will take the data CGPA and placement, and we will plot it as a scatter plot using a code, and we will plot first our regression line where we will change the m and b coefficients to see how this regression line is moving. And then next we will first find the optimum values of m and c using scikit-learn linear regression library. Okay, linear model library, so that our error function is minimized. And next what we are going to do is make the algorithm behind the scikit-learn library by ourselves from scratch. Okay, so let me take you to the code first. uh, yeah, this is a Kaggle notebook, and I have this placement data set. Okay, so first I have imported the data sets, and it is this is how this data looks. It has two columns, CGPA and package. And next I have plotted this CGPA column and placement package column in a scatter plot. So you will notice that as the CGPA is increasing, the placement is also increasing. Okay. So now what I have done is I have taken uh, input as m, that is the slope, and b as an intercept, and I have tried to plot 2 points using this to create a line, because we need at least 2 points to create a straight line. Okay, so this is the equation of a straight line, or this will be the output function. Placement will be the output when we put m into CGPA1 plus the value of our intercept in it. So basically what it is doing, whenever I give it a new CGPA based on the values of m and b, which is the optimum values which we will find later, it will predict what will be the placement of that student based on a CGPA. Okay, so this is the code, and this is my regression line based on this data. But this is not the optimum line. If I change the value of m, you will notice that my line is shifting downwards or upwards. So if I take my regression line as the slope as 3, you will notice if it will shift. See, uh, it is not visible here, but my line has shifted upwards due to the change in its slope. Okay, and now if I change my intercept value, this line will shift downwards or upwards. If I take 4 point, uh, mm, let's say 4. Yeah, so you can see when I'm changing my intercept value, the line is parallelly shifting upwards or downwards. This is due to the change in its intercept. The slope is similar, but it is changing its intercept. Okay, and when I change m and take b constant, it is a pivot point like this, and my move the regression line moves like this. Okay, so now I import the linear regression library from sklearn, and I create a class of it as LR. I uh, X is my input column, that is the CGP, and Y is my output column, which is the package. And this is how X looks. It has 19 rows, and I fit my model. I give pass on X and Y to my linear regression model, and it calculated the optimum value of coefficient for which my error will be minimum, and the coefficient is coming out to be 0.50. Okay, our coefficient was, which we took, was it is 1, and the optimum value of coefficient is 0.50, and the intercept value is minus 0.63, for which the error will be minimized. Okay, so uh, and if I plot these points, if I plot my regression line using the value of m and b, which my model, the linear regression model, has given me, this will be my new regression line, and this is the only line which will minimize my error, which will for which my error will be minimized. Okay, it will be the my error will be most minimum. Okay, so I have taken m as 0.50, which was this value, and intercept as minus 0.63, which is my intercept, and I have plotted this regression line on my scatter plot. Okay, so now what are we going to do is build this linear regression class from scratch, and it is this model will be for only one input column and one target column, that is simple linear regression. Okay, so let's continue. What I have done is created a class called linear regression, linear reg, and I have set the value of b and m to none. Okay, so what I've done here is my when I fit my linear regression model, you will say here I am passing two things. One is my input column and one is my output column. Okay, so I have replicated that here. When I am fitting something in my model, I will pass two things, x and y, that is input and output. Okay, so now what our goal is to calculate the value of m and b, which will help me predict any point or any input CGPA for which I can predict my output, and it will be based on two things, m and b. Okay, so we have already seen what is m. Yeah, m is yi minus y mean multiplied by xi minus x mean whole divided by xi minus x bar square. What that mean is, if I have CGPA and I have my package. Okay, so if my CGPA is 6, my package is 8 LPA. If my CGPA is 5, my package is 3 LPA. If my CGPA is 9, my package is 12 LPA. So what this how we will see how M is calculated. It is yi, that is the output. 8 minus mean of these, suppose it is 7 LPA, multiplied by xi, that is 6, minus mean of this column, suppose it is 8, whole divided by xi minus x bar whole square, that is 6 minus 8 minus 2 and square, 6 minus 8 whole square, plus for second 3 minus 7 into 5 minus 8 upon 5 minus 8 whole square, plus yi, that is 12, minus y mean, that is 7, multiplied by xi 9 minus mean of this column, whole divided by xi minus x bar whole square. So when I calculate these values and take a sum of these, I will get my m, that is the coefficient. Okay, so this is what I have replicated here in my code. M equals to y minus mean of y multiplied by xi minus mean of x, and taking the summation of these terms divided by xi minus x bar whole square, and summation and calculating its summation. Now my b is, we have seen the formula, b is equal to y, mean of y minus m into mean of x. So suppose after calculating this formula, my m value is 1. Okay, so what this formula says, I take the mean of my package column, that suppose it is 7, minus m, that is 1, into mean of my CGPA column, that is coming out to be 8. So m equals to 7 minus 8 minus 1, and this is how b is calculated. So here it is, mean of y minus m into mean of x, and after I have calculated my m and b, I can print my coefficient and I can print my intercept value. And for prediction, uh, what I have done is placement equals to m into CGPA plus my b. So I have my m, I have my b, and whenever I give my model a new CGPA, suppose 8, so it will have the m value and it will have the b value, and based on that, uh, plus 0.5, it will give me my placement or the package. Okay, so this is the code for that. Package equals to m into CGPA plus my intercept, and it will give me the package which I could uh, uh, hope to get based on my CGPA. So I created my class linear regression as 11. I fit x and y, that is my input column and output column in this class, and these are my coefficients 0.50 and minus 0.63, and you can verify this looking on the scikit-learn's coefficients and intercept, and you will notice that these are exactly same coefficients which I have calculated from scratch. Okay, coefficient is 0.506 and my coefficient is also 0.506, and this is the same intercept. And to predict the value, I have taken CGPA as 8. This is my prediction function, and when I give it a CGPA, which I has given, it will predict the package I could expect to get. And this is the same value which I am getting from scikit-learn's linear regression algorithm, 3.41 lakhs per annum. Yeah. So we have completed this part and we have created our own library from scratch to predict the package based on the CGPA of a person, and it exactly matches the scikit-learn's internal working. But and in now in our next part, we will cover how this model is built from scratch when we have more than one input column. That is, suppose we have a column CGPA and now we have a column named IQ to predict the package. Okay, so thank you for watching this video. Hope you like this and suggest anything, or if you find some error, please let me know. Thank you so much.